Now that we have a couple of different reactions in our repertoire, we can start to talk about the concept of synthesis in organic chemistry. And in particular, synthesis is the use of multiple sequential reactions to accomplish a transformation that we can't do in a single step. For example, if we wanted to start with a cyclohexanol and turn that alcohol group into a thiol, that's not something that we can do in a single step. What we can do, though, is think of a series of reactions that we could use to make that happen. And it's actually going to be helpful to consult that reaction chart we talked about in the very beginning of the chapter, because it shows us our different functional groups. We can find alcohol, we can find thiol, and then we can find the series of transformations that are necessary to make that happen. For example, the alcohol can be converted to an alkyl halide. The alkyl halide, in turn, can be converted to the thiol. So we can use that sequence of reactions on our starting materials, or starting material. So alcohol converts to alkyl halide. We could use a Br, and that could be accomplished with HBr or PBr3. And then to add the nucleophile, we would need this piece basically as an anion with a salt or a counter ion present. Now, also introduced in synthesis is the idea of retrosynthetic analysis, which is essentially thinking backwards from the product. And we even have our own arrow that deals with that. So what we would do is have the product here and use a double-tailed arrow that basically means can be made from. And then we'd think about, well, what do we make the thiol from? Well, the thiol, according to our reaction chart, right, we could make from an alkyl halide, like a bromide. The alkyl bromide, in turn, can be made from our starting material. So now we're back to our starting material. Now, this approach can be used to deal with stereochemistry as well. So let's take a look at another example where we want to be stereospecific. Here we want to start with a chiral alcohol, S2-butanol, and we want to make the corresponding alkyl bromide, specifically with inversion of stereochemistry. So pause the video here and take a few minutes and see what you can do. One option, of course, would simply be to use HBr with our starting material. But remember, because our leaving group is secondary and our starting material is protic, we are at protic conditions, we're going to go SN1 for our mechanism, and we would expect to see both the product that we want, where the bromine is inverted relative to where the OH was starting with, plus the other enantiomer. So a better strategy in this case would be to convert the OH into a leaving group that can be reacted under aprotic conditions. And an excellent choice here, really the only one we know of, is the tosylate. So we can add the tosyl group in place of the hydrogen, conserving stereochemistry, because the substitution is happening on the sulfur of the tosyl group and not on the chiral center. Then we want to add bromides, so we need Br-. We'll use it as a potassium or sodium salt. And we want some aprotic solvent, maybe some diethyl ether. You pick your aprotic solvent of choice that you want to remember. It could be diethyl ether, THF, DMF, DMSO, acetone. Any of those are great polar aprotic solvents. So again, we've managed this transformation stereo-specifically and get mainly or exclusively the stereoisomer that we wanted.